So basketball coaches have this thing they like to say, which is that basketball is a game of runs. And what they mean by that is if a given team goes up scoring 2 points and then scores another 2 points, then they're more likely than they normally would be to score a third basket. Now, once this team's up, if this team scores, then they're more likely to score again and again, basically causing these long runs. Now, my question was, is this true? Once you score a couple baskets, are you really more likely to score the next basket? Or is it just humans seeing patterns in random data? So I found this paper that addresses this question, is basketball a game of runs? Is by looking at the longest run of field goals by the same team in each game and comparing that to what you would expect to see if scoring events were completely independent. So what you can see here on the x-axis is the longest run of a given game, and these are the number of games with that longest run. And the blue is the observed in the data, and the orange is the predicted based on if it was independent random events. What you can see is the blue and the orange mirror each other very well, and he says this: the fit of the null model to the data is excellent. A chi-square goodness of fit test gives a non-significant p-value of 0.38. He's basically saying that there's no evidence that there is dependence or momentum in NBA games. But this bothered me because he only looks at the longest run length. What if there were shorter runs that were more frequent than you would expect, but that weren't showing up in this test that he gives here? So I decided to download the data and investigate it for myself. In the same play-by-play data that Professor Schilling used, I wrote a program to determine whose possession it was at all times. So this is what the play-by-play data looks like. And I wrote a program that looks at each event and figures out whose ball it is based on the data. Writing that program allowed me to see this. It allowed me to see one team, in this case the Warriors, all their possessions against all the other teams. So in this case, others score, then the Warriors score. Then the Warriors stop, then the Warriors score. This allowed me to get two values. One was the probability of a Warrior scoring on any given possession that they had the ball. Okay? And it also allowed me to see the probability of them scoring, like here, after they just got a stop. So we'll call that probability stop score. Now, I could compare these two values, and if this one was significantly larger, so if they were more likely to score after they just got a stop, then it was evidence of dependence and therefore proved that there was momentum. Okay, so this is the actual data for the Warriors. Here you can see the probability of them scoring on any given possession that they have, and this is the probability of them scoring after they got a stop. So you can see here that the probability that they scored after they got a stop is slightly higher, and the question is it significantly higher? And that's what I'll answer next. Here you can see the probability of scoring and the probability of scoring given you just got a stop, which is equal to the number of stop scores over the number of stops. We're going to assume that this is the true value for scoring. This is not a safe assumption, but it just helps us figure out what are the possible values that we would expect for the stop scores. We need the probability mass function of the stop scores given n number of stops and a p of probability score 0.42. So if we were to just draw that out, it would look like this. N equals number stops and p equals probability scoring. Once we have the probability mass function, which in this case is going to be the binomial distribution because you can either get a score or a stop. So it's only two options, and we're assuming that each trial is independent. Using the formula for the PMF of the binomial distribution, which is F NKP equals, now we need to know, okay, I got this value here, which is number of stops, or which we can also call it K. Now I need to know what is the probability of exceeding that value, okay? The way you figure that out is you just do 1 minus the cumulative distribution function of, once I figure out this value, then I know the probability of exceeding the value I've got for K, and that's going to tell me the odds that my result wasn't due to chance. So now if we do just like we said, which is plug in the values for these variables here, then we can put them into the cumulative distribution function like I just did, do 1 minus that, and we should get the significance of our result, which is 0.019, so pretty good. So there's a 2% chance basically that the result that we just got is due to chance. But we have to remember that right now we're taking this p-score value as a true value, and it's not. It's a random variable as well, so we have to tackle that now. So now we need to see, given this value that we got here for the probability of scoring, or what are the range of values that we can expect. The way I determine this is you say given n possessions and given k scores, what would be the probability p that makes this cumulative distribution function? What would be this value p that would make it equal to 0.01? So graphically, so this is given n and k, what would be the p that makes it so that this area here is equal to 0.01? Once we figure that out, then we can just get this expected value here, and we can use that instead of probability score to then figure out this stop score calculation that we just did. And then we can really see if we got a significant result. So I have actually yet to figure out how to get this p-value. So that's kind of the next step. But one more, there's another thing I also wanted to point out that we do have to take into account. So even if we were to get a significant difference between these two values here, the problem would be you can't actually tell why there's a difference. What I mean by this is when I'm getting this value here, I'm pulling from a subset of possessions where the Warriors got a stop. This means that I'm pulling from possessions where the Warriors were more likely to get a stop. Okay, and that could be because of a worse team. That could be because of a better matchup for the Warriors. It could be because the Warriors were at home, etc., etc. Then, all three of those reasons, you would then expect them to be more likely to score. But that's not really what we mean when we say basketball is a game of runs. We don't mean you're more likely to score against worse teams. That's obvious. What we mean is given a specific team on a specific night, and given that you just got to stop, are you more likely to score? So what you really need to do to figure out this question of is basketball a game of runs is you need to look at each individual game. You need to see the probability of scoring on that game, the probability of getting a stop and getting a score on that game, and you need to compare that for each individual game that a team plays. If you consistently see a significant difference between those values for every single game, then you can actually say that basketball is or isn't a game of runs. But the way Schilling and the way I was doing it to start do not actually answer basketball as a game of runs. It's more like answering, is basketball a season of runs? So that's kind of the next step in the process of figuring out this question.